Thank you for that. I'm Luka. I'm part of the ACSD group. And today I'll be talking about a software framework that we developed called AutoTandemML that is designed to solve inverse design problems in science and engineering. Okay, so our first motivation here was the efficient training of machine learning models, but purely from a data perspective. So what I mean by that is that we want to determine an optimal or specific data set that yields the maximum accuracy of our machine learning model. So instead of like randomly sampling our experimental solution or our very expensive high fidelity simulation, especially when resources are limited, we don't want to do that, and we want to focus on determining this subset of data. We're going to do this with active learning, or our software does this with active, which is a technique that I'll explain a little later. The next problem that we want to solve is the problem of inverse design. So with inverse problems, we start with the effect and we want to determine the cause. Unlike forward problems, where we start with the cause and we want to determine the effect. And these problems are usually very challenging, like very, very hard, especially when we're trying to map this inverse relationship between our effect space and our cause space. Sometimes in our effect space, we have multiple points that map onto a single point in our cause space. And that's very challenging. This is the problem of non-uniqueness. And this is a huge problem, especially for training machine learning algorithms mathematically. We also have other methods here like optimization algorithms. They have their own drawbacks and their benefits, but we're interested in ML right now because we want to get like a really quick solution for our inverse design problem. Okay, so as I said, to solve the efficient data generation problem, we're going to use active learning. So I want to introduce supervised learning first, and I want to contrast it to active learning. So supervised learning is basically your most basic vanilla approach to machine learning modeling nowadays, where you have this huge, the larger the better data set that's static, where you don't add anything in the process, but it has properly labeled input data and properly labeled output data. And like you do here, you throw a machine learning algorithm in between, and what it does, it essentially just maps the values, for inputs to outputs, just tries to capture this relationship between the two. But with active learning, we have things working slightly differently, where we have basically a loop where we're creating this data set iteratively. So what we're doing here, we're simultaneously training our machine learning models and generating our data that essentially yields the maximum accuracy of these machine learning models that we're training. So instead of, like, as I said, randomly sampling our experiment or our simulation, what we do here is we determine the points for which our model is most uncertain about its predictions. So we're trying to find the points of maximum uncertainty. So we find these points, we throw them at our experimental setup or simulation, and we get our responses or results, and we update our data sets, and we retrain our models. This is the process of active learning. So we're actively adding new labels to our data instead of having this large static data set, as in like classic vanilla supervised learning. Okay, for the inverse design part, for that problem, we're going to use tandem neural networks, which are like they're a deep learning solution tailored for inverse problems. Essentially, they're very modular. They consist of two segments. So once we have like a well-defined established data set of our problem, firstly, what we do, we train a forward DNA that maps the x's to our f of x's. And once we have an accurate forward DNA, we train our inverse DNA. So what happens here, we reverse our inputs and our outputs. So we map our f of x's to our x's. And in the loss function during this training process, what the forward DNA is doing, it's actually seeing if the predicted x value, how close it goes to the input f of x value of that training instance. And this measure is basically the value of our loss function. And if you remember, I mentioned the non-uniqueness problem. We don't solve it really, but we go kind of around it in this way, and we can probably properly tune the weights of our neural network to capture this inverse relationship, essentially. Okay, so we created this software framework that combines the efficient data generation part with active learning, and then we do the automatic tandem neural network generation, essentially with some architectural searches, like with some optimization here. The neat part here is that essentially the user just needs to have some kind of connection to their experiment or their simulation through a simple Python function. So we just need to get the f of x's from your experiment given some specific set of x's, essentially. Also, it's designed for high throughput experiments. We have some novelties here that include batch selection of these sampling points because we don't want to do things sequentially, essentially. Okay, we also created this benchmark suite for inverse design problems, or like benchmarking inverse solutions for for machine learning models. It's called Inverse Bench. It consists of 3 different black box inverse design problems. One is the inverse design of an airfoil, which is like a classical inverse design problem. You also have a photonic surfaces inverse design problem, which is essentially a metamaterial inverse design problem. This is actually our own data set that we got from the ETA. We're designing photonic surfaces with them using tools like this. And it's actually important to have this kind of problem because this community has been pushing inverse design a lot lately, like specifically metamaterials research community. And we also have a problem that's like a scalar boundary construction problem where we try to determine the boundary condition of a 2-dimensional PDE based on a set of sensor measurements. This can be applied to determining the pollution of based on a set of sensor measurement in groundwater flow, something like that. We also created this to benchmark our own solution and, for the broader research community to test their own solutions. Finally, some results here that we have from this automated framework. Essentially, we have 3 benchmarks here, 3 different figures. On the y-axis, we have the worst, let's just call it the worst normalized error, which is essentially a metric that's like a gold standard in active learning by some researchers, at least. On the x-axis, we have different approaches that differ only in the way that we generate the data set to train these TNNs. Our solution is the orange one. We repeated the runs. We repeated the runs for every method for 30 times to account for some randomness. And these box plots, they capture a lot of statistical information, but the gist is essentially that it should be as low as possible and as narrow as possible. Actually, in our method, beats every other method on 2 benchmarks and is competitive on the 3rd one, which is the scalar boundary one right here. And also all of these other methods we have implemented in our own software framework. Yeah, and finally, we're already testing this with the ETA people in the lab as a self-driving lab solution, essentially. It's in test mode. We're about to close this loop very soon. We also just want to throw this framework to any kind of inverse design problem that kind of fits this criteria of like efficient data generation and using tandem neural networks and just see how it performs because we have only tested this on controlled problems. And we also want to extend this to multi-objective optimization. When we create these surrogates, we want to use them for multi-objective optimization because those are most realistic, in problems in science and engineering problems. Help. Yeah. Thank you.